Hello world, it's Rational Pi, and we're here today to talk about computer complexity or algorithm complexity. And this is my favorite unit of all time in any sort of engineering, computer science, whatever. It's called the FLOP, or it stands for Floating Line Operations Per Second. So FLOPS, excuse me. And that's what's used to decide how fast something is operated on. Like, for example, I have a 2.8 gigahertz 4-core that runs 4 flops. And so what you do is you take 2.8 times 4 times 4, and that's what gives you the amount of gigaflops that your computer can perform. So that roughly equals out to 29.7055 for my computer personally. So what I wanted to do today is go over some various complexity numbers and show you why n factorial for the traveling salesman problem is a ridiculous problem. So let's go ahead and take a look at that first. So my computer again runs 29.7055 gigaflops. And once you get to about, I don't know, let's see, 17 nodes, it takes my computer roughly 3 hours to perform that. Okay? But let's go all the way down to, let's say, 30 nodes. That would take me roughly 2.83 times 10 to the 14 years, or 20,000 times the age of the universe. So if I wanted to perform the traveling salesman problem with my computer, I better have a long time, and probably by then the Earth will be destroyed. But let's take this one step further. Let's go down to 100 nodes. It would take me literally a magnitude of 129 times the age of the universe for me to perform this on my personal computer. So, Dropbox, what are you talking about? My space is low. Leave me alone. Anyway, so let's take that and use the theoretical maximum my computer can perform, which is 44.8. And it really doesn't help a whole lot. Because once you get down to 27 nodes, it takes about half the time the universe has been in existence. For anything to be feasible, let's say in hours, it'd be in 17 nodes, which is 2.2 hours. The maximum gigaflops that has ever been recorded actually isn't recorded in gigaflops. It's actually 33.86 petaflops, which is 10 to the 15th. So let's see, if we wanted to run an algorithm with n factorial complexity, how that computer would do. And this is the strongest, by far, computer in the world. Well, it does considerably better, because you can get 23 nodes in roughly 8 days. But again, if we wanted to do 30 like in our MBA, it's going to take about 1% of the age of the universe, or 2,484,085 centuries. So there you go. It's ridiculous. But let's go ahead and take a look at some other complexities out there. One of the other more ridiculous ones is 2 to the n, which is, coincidentally enough, another algorithm that we did earlier on in our Let's Code series, the Fibonacci algorithm. If you use the recursive method to find the Fibonacci sequence, then it's actually a 2 to the n algorithm. So, but it's not near as crazy. Like, for example, for 30, it's roughly, I don't know, 1 billion. Yeah, 1 billion? No, 1 trillion. Billion? Trillion. Whatever. But here it's 2.65 times 10 to the 32. So it's not near as complex, but it still gets pretty damn complex because once you get to about, let's go to 100 nodes. It's going to take us roughly, this is hours, it's going to take us, this is days, years, 97 times the age of the universe. For 1 year, it's going to be about 60 nodes, yeah. And then for a day, it'd be about 51 nodes. For an hour, 47 nodes. So, as you can tell, the 2 to the n kind of does this. And we'll see that later. Let's take a look at another one, n squared. This one's a lot more manageable, and you can perform 100 nodes in roughly less than a second. And then you got n log n, which is going to be even more fast, so it's considerably less than a second. I'm kind of intrigued to see how far this can go before it even reaches a second, so let's just go crazy here. I guess I could have done something a lot easier than that. I don't know what the hell I'm thinking, but let's just do this. Roll down 1, roll down 1. Let's make it 10,000 nodes. Not even close to a second. Oh, there's a second. 4, 5, 6, 7, 8, 9, 10. Okay, so there's about 7 seconds, and you needed 10 zeros. So that's how long it takes to get 7 seconds worth of n log n. So you can do a lot of nodes if the algorithm is n log n. So let's go ahead and take a look at that in a graphical sense. So on the top here is the number of nodes at the bottom, and up here is the number of seconds involved. As you can tell, the n squared and n log n aren't even going to register because at about node 31, the n factorial just shoots up, and it goes way past 1 times 10 to the 19th. And then all the way over here, about node 93, is when it really starts growing exponentially here for the 2 to the n. So you're not going to really register these bottom two ones, but down here is a more viable graph to kind of show you how many operations. Wow, I was horrible with my formatting on this. So this is again the number of nodes. Number of nodes. I guess there's no of there. And this right here is the number of operations. So as you can tell, n log n is going to take the least amount of operations to do 100 nodes. Next up is n squared. It's just going to keep increasing. And then it's 2 to the n, and then n squared. Or n factorial, excuse me. And so this kind of puts into perspective that you want to make an algorithm that can fall within a polynomial time, because as you can tell, n squared or n log n is a lot more manageable on a computer such as mine, or even on a supercomputer, as we noticed before, than if we wanted to try to do something on n factorial level. And that's the key part of the n or PNP problem, is that we don't want to have to keep using these n factorial algorithms to try to find something that can be verified pretty simply. So if we can find a way to perform these operations, to perform these algorithms in a polynomial time, you can tell the reduction in complexity is monumental. And that is the reason why this is such an important part of computer complexity theory. And if we can find a way to either prove, disprove, or even prove that it's not able to prove, this is a huge step forward in computer science. So what I'm going to do next is I want to show you the prime factorization problem, and that will be our next video. I will try to do a TSP problem with 4 or 5 nodes, and I'll show you how to clock your code to see how long it takes to actually perform, and we'll see how these theoretical numbers shape up to the numbers that I actually get on my computer. So that's what we'll do on our next video. A like and subscribe is always appreciated. I forgot Pinkie Pie. She is right here. She says like and subscribe. It really helps the channel out. And I'll see you guys in the next video. Have a good one.